Ever stop and wonder, why is gold gold? Or why is the air you're breathing right now so completely different from a glass of water? For like thousands of years, we've known the answer is hiding somewhere inside the atom. But figuring out what that inside actually looks like, well, that's been one of the greatest detective stories in the history of science. So let's get into it. Let's trace the clues and crack this case.
So this quote really gets to the heart of it. The whole shebang, why some things rust, why others explode, why we can even exist, it all comes down to what's going on inside the atoms of different elements. This is our central mystery. It's the whodunit we're here to solve. What does the inside of an atom actually look like, and how in the world did we figure it out?
All right, to kick off our investigation, we've got to rewind the clock. I mean, way back. Back to a time when the atom wasn't a scientific fact at all. It was just an idea, and a pretty simple one, really. So let's start with the name itself. The word atom comes from the Greek atomio, which literally means uncuttable or non-divisible. The idea, dreamed up by early philosophers, was pretty straightforward. Imagine you take a piece of something and you cut it in half. Then you cut that half in half, and so on and so on. Eventually, they figured you'd get to a tiny, tiny piece you just couldn't cut anymore. That final, fundamental particle, that was the atom. Just a solid little uncuttable ball.
But here's the crazy part. For almost 2,000 years, this was just a cool thought experiment, a philosophical idea. There was literally no way to prove it. The idea just sat there gathering dust until 1808. That's when John Dalton, a school teacher in England, came along and said, "Hey, I think there's something to this." And he was the first person to turn it from a philosophical guess into a real scientific theory.
And let me tell you, Dalton's theory was a smash hit. It was amazing. It perfectly explained all these fundamental rules of chemistry that people were observing. Like the fact that you can't just create or destroy stuff in a chemical reaction, you just shuffle the atoms around. So in Dalton's world, the atom was still that tiny, solid, indivisible particle, and his model worked beautifully for a while.
But there was this one little nagging problem. A really simple thing that just didn't make any sense. Like, how do you explain static electricity? You rub a glass rod with a piece of silk, and suddenly it can pick up little bits of paper. It's charged. But if atoms are these solid neutral things that can't be broken, where does that charge even come from? This little observation, it was the first loose thread. And once scientists started pulling on it, the whole idea of an indivisible atom was about to completely unravel.
In that first clue, electricity was about to spark a total revolution. It was going to give us our very first peek inside the atom. Okay, so fast forward to the 1830s. You've got the legendary Michael Faraday in his lab, zapping different chemical solutions with electricity. And he notices something weird. As the electricity flows, stuff starts happening. Chemical reactions, little bits of metal plating on his equipment. This led him to an absolutely mind-blowing idea for the time. What if electricity isn't some kind of invisible magic fluid? What if it's made of particles? Little bits of something.
That single idea kicked off one of the most important experiments ever. Here's the setup. Scientists took a glass tube, sucked most of the air out, and then blasted a super high voltage across it. And when they did, bam! Something started streaming from the negative end, the cathode, over to the positive end. You couldn't see these cathode rays themselves, but they put a special screen at the other end of the tube, and wherever the rays hit, it glowed. They had found something, a mysterious, brand new particle.
And hey, this wasn't just some dusty old lab experiment. You've actually seen this in action. You know those big old clunky TVs from back in the day? The ones that weighed a ton? They were literally just fancy cathode ray tubes. They were painting the picture on the screen by firing these very same particles at it, line by line.
And that particle, that mysterious glowing particle, was the electron. It was incredibly tiny, it had a negative charge, and this is the absolute kicker. It came from inside the atoms of the metal plate. This was it. This was the moment the game completely changed. The atomio, the uncuttable, had been cut. The atom wasn't the bottom floor. It had a basement.
Okay, so hold on. If atoms have these little negative bits, these electrons, flying around inside them, but we know that atoms, overall, are neutral, then there has to be some positive stuff in there too, right, to balance it out. So what did this new atom actually look like? Well, it was time to go back to the drawing board.
The first guess came from J.J. Thomson, and it's famously called the plum pudding model. Just picture a blob of positively charged dough with the little negative electrons stuck in it, like raisins or, well, plums in a pudding. It's a nice idea, but it was totally wrong. Ernest Rutherford came along and proved that all that positive stuff wasn't spread out at all. No, it was all packed into an insanely tiny, super dense core right in the middle, the nucleus. And the electrons? They were orbiting way out in the boonies.
So Rutherford's model with the nucleus was a giant leap forward, but it still didn't explain why different elements behave the way they do. The plot was about to thicken, though, because the next big clue in our detective story came from somewhere nobody expected. It came from light. So check this out. When you heat up a gas until it glows, you might expect to see a full rainbow, right? But you don't. Instead, you see these sharp, distinct lines of color. It's like a unique barcode for every single element. It's their atomic fingerprint. And get this, if you shine a white light through that same gas when it's cool, it sucks out, it absorbs light at the exact same frequencies, leaving black lines. It's like the photographic negative of its barcode.
This new tool, spectroscopy, was an absolute game changer. Suddenly, scientists could analyze the fingerprints of light coming from anything and identify the elements inside. They started finding new elements left and right. But the most incredible discovery of all? They pointed their instruments at the sun, analyzed its light, and found a barcode for an element that had never been seen on Earth. Can you imagine? They named it helium, after Helios, the Greek god of the sun. They discovered an element on the sun before they found it here.
But this just led to an even bigger question. Why? Why specific frequencies? Why a barcode and not a smooth, continuous rainbow? Rutherford's model, with electrons just whizzing around the nucleus like little planets, had absolutely no way to explain this. This barcode of light? It was a secret message being sent from inside the atom, a code that held the key to everything. And that, my friends, brings us to the final chapter of our story. We're about to crack the code. This is the solution not just to the mystery of the light, but the key that unlocks pretty much all of modern chemistry.
The answer, the secret code that explains it all, is something called electron configuration. This is it. This is the master blueprint that dictates why atoms act the way they do, why they stick together to form molecules, why anything is the way it is.
So, what on earth is electron configuration? Well, the modern quantum model throws out that whole electrons as planets idea. It turns out electrons can't just be anywhere. They're stuck on specific energy levels, or shells. Think of it like a weird apartment building, where you're only allowed to be on the first floor, or the second floor, or the third, but you can never be in between, floating in the stairwell. And those barcodes of light? That's the energy that gets released or absorbed when an electron makes an instant jump from one floor to another. That's why you get specific lines. It's the exact energy difference between the floors.
And this one idea, these electron shells, it answers all those big questions we had at the beginning. It really all comes down to the electrons on the outermost floor, the so-called valence electrons. Think of it like this. Every atom wants to have its outermost floor completely full. It's their one big goal. An element like helium, its outer floor is already perfectly full. So it's happy, it's stable, it doesn't want to mess with anyone. That's why it's so unreactive. But then you have something like the halogens. They are one electron short of a full floor. They are desperate, they will do almost anything to grab that one last electron to feel complete, which is what makes them super reactive. This one simple rule explains everything. Why atoms bond, why the periodic table is shaped the way it is, everything. The case is closed.
So think about the journey we've just taken. We started with this idea of a tiny, solid, uncuttable ball. And where did we end up? With a model that's, well, mostly empty space. A tiny nucleus in the middle, and then a whole lot of nothing before you get to these electron shells. Our atoms are shockingly, overwhelmingly empty, which leaves us with one final kind of mind-bending question to chew on. If you and me and the chair you're sitting in and the entire world are all made of atoms that are 99.999% empty space, then why does anything feel solid at all? Why can't I just walk through a wall? Now that is something to think about.